All right. Hello and welcome everybody to ClearCalcs Learning Hour with Python Fixings Australia. We are just getting people into the room now. If you would like, just say hi in the chat. Let us know what is your name, your title, and where you are tuning in from. That is your company and city where you are at, so that we can get to know you. And then we will start with a quick introduction, and then we will have a session with Kieran from Python Fixings to talk about the topic today, remedial and retrofit of masonry structures. All right, quick one from me. We are co-hosting this with Python Fixings. We are ClearCalcs, a company founded in Australia, but we have operations across the United States, Europe, Australia, and New Zealand, as well as Canada. We have a team out of Melbourne, in Toronto as well, and quite a few structural engineering team out of Bogota in Colombia. Our projects is scattered across everywhere. As you can see on the map to the right, these are our customers' projects. We are running about 70,000 projects every year, ranging from residential to light commercial and industrial designs. What we are here for, we are here to help engineers solve three things. If you need to calculate your design and analyze them, whether that is existing materials like wood, timber, steel, and concrete, or something new like cold form steel. If you want to connect and automate your process so that you don't have to copy and paste your calculations, for example, and if you want calculations that are accurate, code compliant, so that you can deliver something that is accurate to your clients and customers. How we help, we have off-the-shelf calculators. These are pre-built calculator library to different types of members like beams, columns, and footings. We cover timber, steel, cold form steel, and concrete. And we also have coming up in the next 6 months to help engineers go further with their calculations and tools. We are releasing our no-code and drag-and-drop calculator builder, as well as the ability to integrate your calculations library with your existing tools and project management platforms. So I've covered this one, so I'm going to skip this slide. So just a quick housekeeping. If you have any questions, just make sure that you ask your questions in the questions tab at the bottom of your panel. And then you can also upvote your favorite questions, because we will answer them in order of votes that we are getting. And we will address all of these questions in the second half of the webinar, around 15 to 20 minutes at the end of the session. All right, that is all that I have. Thank you, everybody who's dropping in your intros. Good to see everybody joining from Sydney, from Melbourne, from WA, a few from WA as well. I am in Perth, and we've got even someone tuning in from Vancouver, Canada. That's unusual. All right. Without further ado, I'm going to hand this over to Kieran. Kieran, the floor is yours.
Awesome. Thank you very much for the introduction, Ati. And yeah, thanks everyone online for your time today. Really appreciate it. Also, a huge thank you to ClearCalcs for the opportunity to run this seminar. We really love getting involved in things like this, so really grateful for that. Thank you. Alrighty, so I've actually met a number of you already in person, having a look at the attendees list there. But for those who I haven't met thus far in Australia, I'll give a quick introduction about myself. So yeah, my background is I'm a structural engineer by trade. I started out in New Zealand working as a design engineer for a company called Holmes Consulting, fairly high profile in New Zealand. Through that work, I was super lucky to get involved in some analysis and seismic retrofit of existing masonry buildings, both in New Zealand and internationally. So I did that for about 5 years, and then I made the move to Python because I sort of figured out that's what I was really interested in, the existing building space. Started out in New Zealand with Python, and now I've made the shift full-time to Victoria to really get my teeth stuck into the really exciting retrofit projects that you have going on here in Australia. Right, so yeah, this is not intended to be a commercial presentation. My plan for today will be to run you through 3 sections. So the first part will be a bit of a backstory about where Python came from and what our story is, because I think it's quite interesting. And I'll go through a high-level overview of remediation and retrofit techniques, historic and current, and talk about the most important ones in the Australian construction environment. Of course, I've only got an hour, so I won't get into the weeds with these techniques. But of course, my contact details will be circulated after this. If you'd like any more information on any of the techniques, feel free to reach out. I'd be more than happy to provide you with that. And then the final section will be anchor specific. I'll give an overview of our learnings from our earthquake reconnaissance missions, with specific focus on the performance of the existing anchor types and existing masonry substrates. All right, so without further ado, let's crack into it. So I presume the majority of you online are familiar with the Christchurch Canterbury earthquakes in New Zealand. This was a high-profile natural disaster in New Zealand. There were over 185 casualties, and it really did rip through the city and destroy a lot of the existing structures. From a structural engineering standpoint, the Christchurch earthquakes were actually fascinating. The reason for that is that it was really the first example of a heavily seismically retrofitted masonry building population being struck by a major seismic event. In general, surprisingly, the buildings actually performed worse than expected that had been retrofitted. And as a result of that, a royal inquiry was launched by the New Zealand government. And the 2 engineers who led that royal inquiry later went on to start Python fixings. And that's how Python came about. So interestingly, the cause of the poor performance of the retrofitted buildings was actually found to be due to the type of anchorage systems into the existing masonry that were used. And I'll touch on our learnings with regards to those anchor systems in the last section of the presentation. Cool. So it's not all doom and gloom. It's important to note that when retrofits are implemented really well in these buildings, they do work extremely effectively. So what we've got here on the building on the left, we've got a building, the Christchurch earthquakes, the day after the earthquake, struck by a lot of damage, a lot of it's essentially been ripped apart. On the right, we've got a similar building. It was actually just 2 to 3 kilometers down the road, and that one's been seismically retrofitted. So you've got concrete shear walls and steel braced frames. You can see the drastic difference in performance there. So the building on the left is no longer there, and the building on the right is still standing to this day. Okay, moving on to retrofit systems. So what I'm going to do in this section is highlight some of the retrofit systems that are out there in the industry, both past and current updates to them, and also focus on the ones that are most useful in the Australian environment. And then we'll step through some of the elements of these existing masonry buildings that are critical to life safety from a seismic perspective as well. Alrighty, so the one that pops up here all the time is veneer restraint and corroded wall tie replacement. So a couple of images here to demonstrate this. So what we've got in that middle image there, you can see a corroded tie in between the veneer and the structural backing layer behind. This is a common one that pops up. Unlike in the States, where it's legally required that you inspect your veneer ties every 5 to 10 years, state dependent. There's no such requirement in Australia, and that really adds into this problem. As you'll know, with masonry veneer construction, especially with double brick walls, the intention of those double brick walls is to provide a moisture barrier to the buildings, and so you do get significant moisture buildup inside these cavities. All that they really used to tie the 2 layers of masonry together back in original construction were flexible wire ties with no corrosion systems on them. And as a result, they generally tend to be corroded, and it's sensible to assume as such in your design if you can't inspect them sufficiently. One to look out for is this image on the left. So this is actually lime mortar construction. The key thing to know about lime mortar is that it's quite porous relative to cementitious mortar. and it actually allows water ingress, and water can sit in the bed joint of the masonry unit and hold there. And so you might put a boroscope or visually inspect the ties inside your cavity and appear that they're in okay condition. But actually, upon removal of a brick, you may notice that because of the water pooling in that joint, the tie has completely disintegrated where the mortar is. So that's one to be aware of. So here are a couple of examples where veneers have failed due to corroded cavity ties. So the image on the left is actually from the 1989 Newcastle earthquake. And the image on the right is an image from Christchurch, where you can see the ties were clearly corroded and the veneer has fallen away, just leaving the structural backing layer behind. Of course, there are various systems for retrofitting these corroded cavity ties. There's good ones and not so good ones, and I'll touch on those various systems in the last section of the presentation when we get into the specifics of the anchor performance and the learnings. Right, moving on to the critical life safety elements in these buildings. So parapets are essentially stacks of bricks around the perimeter of your building, street facing, and they tend to experience the highest seismic loading in the building, being at the highest level. So what we've got on the right here is a graph showing the collapse statistics of parapets from the Canterbury earthquakes. On the y-axis, we've got parapet height, and on the x-axis, we've got the percentage of parapets that collapsed that had not been retrofitted. Probably the most interesting thing about this graph here is that you notice that quite a number of the small parapets actually collapsed when you may have expected that they would have sustained that loading. Part of the reason for that is that the codes actually allow you to assess parapets under a rocking mechanism to dissipate the energy, which is generally sufficient for a short parapet to work. However, one of the key findings from our earthquake reconnaissance work is that there's actually a DPM layer often at the base of these parapets to prevent water ingress into the building. Very sensible. But what you essentially create there is a sliding surface, and some of these parapets just simply slipped off the building rather than rocking under the rocking mechanism that was assumed. So most common one for retrofitting parapets is steel bracing systems. So image in the top left here is quite interesting. So this is post Christchurch earthquakes. You'll see that front street facing parapet has successfully held in place with the steel bracing system. And you'll notice the shorter parapet at the back has actually collapsed in the non-trafficable area. So that retrofit has kind of done its job as it was supposed to. So 25% of the observed steel bracing systems to parapets in the Christchurch earthquakes failed. However, that's a little bit misleading. The bracing systems tend to perform fine, and what was actually going on, if you look at the image below, you've got a failure of an epoxy anchor there, which is a common observation. Otherwise, the wall also commonly failed out of plane below where the parapet was, leading to the parapet failure. So a little video for you now, just play it. So this is investigating different bracing techniques using steel and timber for bracing parapets. So with the steel system, you'll see that it sustains 1.6 G quite easily. And the intent of this was really to prove that timber could be used as an alternative, given how cheap and easy and modifiable it is on site, without the need for any prefabrication, etc. And that also sustained 1.6 G. So timber is indeed a viable solution for retrofitting parapets with a bracing system. One that we've kind of pioneered in the industry is the use of long mechanical anchors for retrofitting parapets. The key thing here is the main intent of this was to remove the complexity and skill and expense associated with core drilling and grouting in bars, which can add up. By the virtue of these being thin mechanical anchors that can be installed just with simple hand tools that every contractor has on site, as you can see in the image on the right there, which definitely removes a lot of the cost associated with that core drilling. Image in the middle is Berkeley have actually jumped on this technique here, and they're working on some design guidance, developing solid design guidance published to the industry, as well as worked examples for this retrofit solution, considering a wide range of different parapets and roof bracing levels and overburden loads, etc. Chimneys. So chimneys, again, chimneys are essentially a stack of bricks at the top of your building. Not always ideal in a seismic scenario. So the image on the left here shows a chimney. I'd say there was about a 50% chance that collapsed outwards, but in this case it collapsed inwards, probably fortuitously. So the common retrofit you see for these, well, there are quite a few, is steel braces again. Key thing that can happen with steel braces, they sort of have mixed results. Having a strut in an angle like this tends to induce a vertical load, which can cause a mortar bed shear failure. And so you often still get the chimneys failing due to that vertical component of the load. However, of course, doing this is a lot better than doing nothing, and you can dissipate that effect by having multiple connection points up the height of your chimney. One that we've seen a lot of success with is actually the use of post-tensioning rods and plates for chimneys to increase the overburden load, to increase the capacity. So I'll show this as-built video first. So this is an as-built full-scale chimney on the left here, and it's been taken to failure, which it sustains about 0.4 G. There it goes. You can see here a design on a heritage building, particularly useful method on a heritage building where the chimney does not have to remain in service, and it has to be quite low profile to not impact the architectural provisions on the site. So video on the right here is a post-tensioned chimney. It's got a rod going down into a concrete base, cast in, just like we see in the image there. And this has been loaded up to 25 kilonewtons and tested. And that managed to sustain 2G, so significant improvement versus the as-built case. Where the chimney does have to remain in use, which is often the case, there is some really interesting research we've been involved in out there, which investigates the use of carbon fiber strips running up and down the outside of the chimney, which can be a viable methodology for strengthening a chimney when it has to remain in use. All right, next critical element that is often addressed in Australia is your outer plane wall strengthening. So we're huge proponents of timber strongbacks. Timber strongbacks are a quick, cheap, and easy way to strengthen your walls out of plane, which are often the critical elements. So, of course, you can just bring timber studs to site, customize them on site easily, install a cleat plate, top and bottom, install anchors, and throw at regular centers, and you've got a wall strengthened out of plane with a lot of redundancy. Frustrating image on the right here. This is from the Napa earthquakes in California. As you can see, you've got a very bad masonry wall out of plane failure occurring on that top level. And interestingly, there's actually a solid bracing system in behind there. Those timber studs have been used just to house the non-structural wall linings. So in some instances, your retrofit solution is already sitting there. If there was some connectivity between the studs and the wall out of plane, it's quite possible that wall would still be standing there today. So here are a couple of the testing videos of this retrofit technique. So on the left here, we have a as-built wall, 3-meter high wall with a diaphragm to wall connection at the top, and that's been shaken on a shake table. Quite a catastrophic failure at a relatively low acceleration. For contrast, here's the same wall build-up, again, diaphragm to wall connection. It's been retrofitted with timber strongbacks at 600 centers. that managed to sustain three times the loading with no failure. So that's about 30% higher than the acceleration of the Christchurch earthquakes. Image on the right is just a reminder that this retrofit technique has been used on a wide range of different masonry types. It's not just applicable to clay bricks. Any modular unit, sandstones, limestones, concrete blocks, clay bricks, it's been implemented in the industry and it works really well. So there was some conjecture when this methodology first came out about how the stiffness would interact when you have quite a flexible building between the timber and the masonry elements. To counter this, what was done was a scale model was built of a masonry building. This model has diaphragm to wall connections, but no other strengthening in place. This is just the as-built case. So that collapses at about 0.25 G. We'll move to the strengthened case now. So what we've got here is a scaled retrofit of the same parameter building. It's got diaphragm to wall connections. It's got steel moment frames on the bottom level, and it's got scaled timber studs on level 1. So this was taken to 1.2 G, and it was actually sustained for 1,000 cycles. So you get some of the elements starting to fail. However, in terms of life safety, there's a dramatic improvement in performance. Cool. In-plane shear strengthening. So this is being done on a couple of high-profile, high-value commercial projects in Australia at the moment that I'm aware of. Quite an effective solution for increasing the strength of a masonry wall in plane. Key thing to note here, well, one of the key considerations of this technique is if you have quite dense reinforcing, large gauge bars closely spaced, you do need to be careful that you're not creating voids in between the masonry and the bars, essentially. That's not too difficult for an experienced contractor with the correct vibration tools to ensure they're doing it correctly. One value add that we've managed to be involved in this space is actually the use of mechanical anchors rather than epoxied in dowels as the starters in between the two substrates. So interestingly, chatting to a contractor a little while ago, we learnt that the cost of the installation of the reinforcing and the reinforcing itself is about 3 times the cost of the concrete. And so that's the key, that's sort of the key driver of the cost on these retrofits. And so we've been able to do a huge value engineering add by getting involved with the mechanical anchors. The speed of installation on some of these projects, if you use mechanical versus epoxied in dowels, has managed to take a lot of time and cost away from some of these retrofits for in-plane shear strengthening. As an alternative to in-plane shear strengthening with concrete shear walls, CLT or plywood overlays are also a good option. So this technique has been used in New Zealand, Canada, and the United States so far that I'm aware of personally. And there's a significant amount of design and test data and reports out there. Comes down to the hold down connections. But yeah, definitely something that is a good option if you need a more low profile, reversible retrofit solution for in-plane shear strengthening. So those are some of the retrofit techniques out there used in the Australian environment, as well as some of the critical life safety ones for these existing masonry structures. We have a mountain of test data and test reports available, both internal, external, collaborations with universities. If any of those techniques are particularly interesting to you, feel free to get in touch after this. I'll be happy to provide you with probably more data than you could ever need to assist with your projects. All right, so moving on to the anchor learnings. So Again, not a commercial presentation, so I'll steer away from talking about our anchors in particular, although of course this is what we specialize in and we're doing some awesome stuff in this space. So again, reach out if you're interested. The key thing here is that anchorage into masonry substrates is quite unique. Masonry is modular, it's variable. You have mortar joints, which may or may not have voids in them. And most of these products that are out there for connecting into masonry come from new construction, rightly so, given that new construction makes up the bulk of the construction industry. And there's varying degrees of technical data available for their application in existing masonry. So this section will go into some of our learnings regarding how these anchor types have performed in existing masonry to date based on our real world reconnaissance missions. All right, so first one, epoxy anchors. We've all specified these, and off the bat, there is nothing fundamentally wrong with epoxy anchors. It's a great system. The key thing with epoxy anchors in existing masonry is it comes down to workmanship. It all comes down to workmanship. So when you're installing an epoxy anchor into a masonry substrate, you come along, you drill your pilot hole. The key thing that needs to occur after that is effective removal of the dust from the hole. This is best done with a vacuum. Sometimes it'll be done with compressed air, which is not ideal in existing masonry. The compressed air in very soft substrates can actually cause more masonry to break away inside the hole, creating more dust, and you end up chasing your tail. So the best way is a vacuum. Of course, if you do put your epoxy in the hole and you haven't sufficiently cleared out the dust, you end up with your epoxy bonding to the dust rather than the substrate, and you don't get your bond. Second thing that can happen, whether it's through inexperience or whatever other reason, is contractor not putting enough epoxy in the hole. Of course, if you don't have your full cross section of epoxy around your anchor, again, you're not going to get your bond. And the final thing that can happen is just each of these epoxies have a set time by the supplier, given by the manufacturer on the data sheet. It's just simply loading up your epoxy anchors too soon before they've had time to fully cure. So the best tools we have to combat this as engineers is QA, but it is genuinely a difficult one to get right in existing masonry, given the generally low compressive strength of the materials we're dealing with. So image on the right there is just an example of an epoxy anchor where there hasn't been enough epoxy put in the hole and you've got a failure. Also this building in the image here, this is from the Christchurch earthquakes. So actually, unfortunately, there was a chef in this building, and when the earthquake hit, he ran out of the building unintuitively. Masonry buildings fail outwards. It was unfortunately one of the casualties in the Christchurch earthquakes, and you can see those failed epoxy anchors up the top there. So the other one that there's been a lot of learnings on lately in the last 5 to 10 years in the masonry space is the use of concrete screw anchors in existing masonry substrates. So the problem with concrete screw anchors in existing masonry is that they tend to be quite short and quite fat. So being short, that makes complete sense in concrete. You don't need a heck of a lot of embedment before you fully develop the capacity of your anchor. However, in masonry, it's generally best practice to use longer anchors and engage as many courses of the brickwork as you can, just to give you some inbuilt redundancy. So this, of course, is to protect against failure modes like what you see in the right-hand image here. So engineers specified a short concrete screw anchor into the first leaf of a multi-wife wall. Due to a poor quality mortar joint around the outside of the wall, in a shake, that whole wall's unfortunately just fallen away, leaving the connection there. Being quite fat, that was the second issue with concrete screw anchors. So what they found once they started testing thousands of these things in the lab is that any mechanical anchor introduces a stress on install to the unit that you're putting it into. And what they found is that the critical diameter around 12 mils and above, you start to significantly increase the risk of splitting your bricks on install, something that you want to avoid. So yeah, in summary, long, thin anchors perform best in masonry substrates. Engage as many courses of the brick as you can, and around 8 to 10 mils max diameters to avoid that brick splitting observation. Helical ties. So I mentioned on the slide talking about the veneer restraint that there's various systems for retrofitting corroded veneer ties. So this is one of them, helical ties. Couple of causes for concern with these things in our earthquake reconnaissance work around the world. So the key thing with helical ties is that they're installed using a supplier tool, which essentially hammers them into the wall. As they're hammered into the wall, they cut their own thread grooves, which are often oversized, particularly in soft masonry. What that means is that under any kind of sustained cyclic loading, whether that's wind, vibration, or seismic, like what we see in the photos, can actually be caused for the ties to wiggle their way around inside the thread grooves as the two wires of the wall oscillate differently, and pop their way out of the wall, giving this porcupine effect, like what we see in the image here. So this building here was an example of a building that had been retrofitted with helical ties, relatively low seismic loading. Ties have been put in at code centers, code spacings, and the veneer is actually pulled away in a seismic event. So URM, last thing on that one. So what we have had seen success with in the industry is actually the use of screw anchors for veneer tie replacement for corroded cavity ties. What you end up getting when you use a screw anchor is you get much better engagement between the thread and the substrate that you're connecting into. And so there's no chance of slip, and they tend to work really, really well for restraining these veneers. URM anchor study, this was done out of the University of Auckland. So to my knowledge, still the largest study undertaken into anchorage systems done anywhere in the world. Over 10 years of research has gone into this. Two key findings from this study. Take a look at the graph on the bottom left there. So you may or may not have seen this detail before, but it's actually mandated in the US codes, believe it or not, for epoxy anchors. So it's a common detail that has been seen across the world in connections into masonry, where you have the epoxy anchor installed at a 22.5 degree downward angle into your masonry, as opposed to horizontal. So when this was tested through this research program, what they found is that it's actually substantially weaker than if you install the anchor horizontal in tension. So a couple of hypotheses as to why that might have occurred. Probably the key thought would be back in the day when they first implemented this detail, the epoxies that were available to use were quite flowable, and it was potentially just to protect against the epoxy escaping from the hole and giving you better coverage around the anchor, like what I talked about before. Yeah, very interesting to me. The bent anchor is substantially weaker in tension than the horizontal anchor. The other key finding from this is the graph in the top right here. So this is related to anchor diameter. So unintuitively in masonry and clay bricks in tension, you actually get a diminishing return on investment of strength with increasing anchor diameter past a certain point. And so you actually, if you look at the graph, you'll notice you get less capacity in a clay brick in tension out of a 20 mil anchor than you do a 16 mil anchor. So the reason for that is that as you're increasing the pilot hole size, you're actually removing more of the material. And what ends up happening is rather than getting a really nice combined cone failure and pull-out failure, which is what you get up to this point, you actually end up splitting the bricks and changing the failure mode to a brick splitting mechanism past around 16 mils. So again, reinforcing the idea that smaller diameter anchors are more effective in masonry substrates. All right, so we got one final video for you guys here. So this is a bonus slide. The previous slides were on anchors themselves and retrofit techniques. This one is actually related to drilling in masonry substrates for anchor installation, particularly in soft masonry substrates. So we actually, this was actually presented at NZSEU, the New Zealand Society of Earthquake Engineering conference last year, and it sent a bit of a shockwave through the industry. So the key thing here is in soft masonry substrates, you shouldn't be using heavy hammer action concrete tools to install your anchors. What you should be using is light hammer action or rotary only drilling methodologies with masonry drill bits to drill the pilot holes. I'll play the video for you now. It's fairly self-explanatory. So it's a heavy hammer action concrete drill. As you can see, you get a big blowout on the back face of the masonry. Quite scary about that is that you often can't see it. Worse than that, you're generating these radial stress cracks around the drill bit. You've essentially shattered any unit that you're putting in this. What you should be using is one of these light hammer action masonry specific rotary only bits, and you don't get that bad failure on the back side of your substrate. So this is particularly bad in your soft masonry bricks, soft clay bricks, concrete blocks, and extruded bricks. It's very important to keep on top of this as engineers from a QA perspective. You can lose up to 60% of your capacity in those worst cases. Cool. Actually, that's pretty much everything from me there. So thank you very much for your attention, everybody. And I'd like to answer some questions if that's possible.
All right. Thank you, Kieran. So everyone, if you have any questions, drop it either in the chat or in the questions tab below, and then we'll get through them. I might just get started with some questions that we received that from the pre-event webinar survey we sent out earlier. A question from Catherine. How do you stabilize masonry that has cracked due to subsidence due to moisture changes in the soil? Do you have any thoughts on that, Kieran?
That's a good question. And so, yeah, cracking in masonry structures is generally caused by settlement. And so you can stitch the cracks structurally using wire products with epoxy systems and then grouting them back over the cracks. But generally that does just redistribute the stresses to another area and you get other cracks occurring across the building. So the best way to address that is to really address the root cause of the problem and strengthen the foundation so that you're not getting that settlement with the shrink swell cycles of the ground.
Yeah, cool. Awesome. I can see a few people typing in, so I'll give them a few minutes to get the questions through. All right, so we've got another question from Bilal. What is the best method to check the masonry wall ties if the rusty tie is embedded under the brickwork?
Yep, that's a good question. So the best way to do that would be to implement a program where you systematically extract a certain number of bricks across various locations, particularly if you think it's lime mortar where this problem might have occurred. So I'd take a sample of bricks out in different locations across the site and inspect the condition of the ties in the mortar joints.
Awesome. Let's see if we get any more questions from the audience. All right, another question is from Ramon. In the past, we use masonry stitching methods and use them as ties as well. Is Python a similar system to that?
Yep. Masonry stitching methods, as in crack stitching. Are we able to elaborate on that question?
I can probably get Ramon to share that a bit more. Let me see. Ramon, if I invite you to the stage, would you able to explain a little bit more on your questions? Or you can type it in the chat as well. Yeah, I can see that Ramon is getting on stage.
Cool. Thanks, Ramon.
All right. Perhaps let's try to answer the other questions first, and then once Ramon is back, we can
Sure.
revisit. Yep. Okay. All right. So I've got a question from, let me see, Alex. For the timber strengthening, are you simply designing the battens to do the job and ignoring the masonry? And do you typically have to design the Python fixing just to the AS3700 wall tie requirements?
Yeah, great question. And so there's actually both approaches have been tested, and there's good research papers both looking at timber studs, timber strongbacks to take the full mass of the masonry wall and do all the work, and then there's also a composite approach that you can use if you need to sharpen the pencil a little bit in the design. So be more than happy to share those research papers with you, Alex, after this. And yeah, just if where there's no specific engineering design, spacings will be adopted at AS3700 spacings.
All right, cool. We've got Ramon online now. Ramon, would you like to explain a little bit more on your questions?
Yes. Can you hear me?
Yeah, I can hear you.
Yeah. Okay. We used to do some rectifications of old brick buildings, and we used a product called Helifix. Is that the same as what Python would be?
Yep. So for brick ties and for crack stitching, we do have systems for both of those.
Okay.
So if you like, I'll send you through some information on what we have for both of those applications.
Yes, please. Well, that will be very
And
interesting for me.
yeah, again, as I mentioned, we've had a lot of success with the use of screw anchors for
Yes.
remediating brick ties that are corroded, just due to the better engagement that you get between the mechanical thread of the screw and the substrate.
Okay, that would be great. If we can have that information, then at least I have two at least different product that I can present to my clients. That would be great.
Yeah, no problem, Ramon. I'll send that through afterwards.
All right,
Thanks.
thank you, Ramon. All right, next question I've got from Masood. What is the max spacing of fixing in AS3700 600 by 600? What about these anchors? If I'm reading that question correctly.
Yeah, yep, good question. So in most instances for retrofitting wall ties for veneers and double brick walls, spacings from tie spacings from AS3700 and the National Construction Code will be adopted, which refers back to AS3700. There's a few instances, us in particular, we have developed a couple of systems which require closer anchor spacings. For example, when you want to compositely connect an outer veneer to an inner veneer so that it works together and gives you an increase in lateral capacity. In that instance, we go closer than the AS3700 maximum spacings. So again, I'd be happy to share that with you afterwards.
All right. Cool. All right. The next question I've got is from Michael. Do you think Australia might introduce a mandatory wire tie inspection like US someday?
I think that's quite possible, given how many of these buildings we come across that do have corroded cavity ties. Although there are triggers in which they do get remediated. Obviously, if you're doing upgrades to the building, remediating or retrofitting it, especially over 50% in Victoria. So yeah, I wouldn't be surprised if that came in at some point in the future.
Nice. All right. Cool. All right. Next question from Jesse. What is the maximum height for the post-tension chimney support?
That's a good question, Jesse. I can refer to the research paper for that. Obviously, it depends how much post tensioning you can get into it and the actual geometry of the chimney itself. So it requires some engineering calculation. But I think they've been done up to about 8 meters is one I can think of that's been post tensioned. So yeah.
Great. All right. Next question from Timothy. A lot of our old houses use the brick walls as retaining for a cut-fill site. Some of these walls have deflected significantly out of plane but are still standing. Any recommendations from you on strengthening and repairs of these?
Okay. Yeah, so out of plane displacement, sometimes you can prop them back into place and then introduce another structural system to brace the wall, like steel posts or timber strongbacks. Otherwise, it depends on how bad it is, the extent of the damage. But sometimes it'll just be a rebuilding situation.
Great. All right. Okay. From Zurich, what is the basis for selecting the spacing of fixings when designing retrofit systems?
Any particular application you're thinking of there, Zurich?
Zurich, if you want to explain that a bit more, whether in the chat or I can also invite you to the stage to explain. All right, let's go through the other questions first, and then we'll get back to Zurich. Let me see, what is the next question? All right, I've got a questions from Adam. If a masonry wall has bowed, will anchoring the two skins together strengthen the wall, or does it require reconstruction to reinstate vertical alignment?
You could potentially prop those walls back into place and then implement some wall ties to give you the composite action that I was talking about for the increase in lateral capacity. And then potentially structurally repoint it to bring it back to its original strength. Again, sort of depends how far gone it is as to whether it might need to be rebuilt, reconstructed, or if strengthening is an option.
Right. Cool. All right, let's go through a few more questions. This one is from Aiden. How do you cater for minimum edge distance of fixing into existing brickwork or masonry if the existing wall properties are unknown?
Good question. So minimum edge distance, we have in terms of minimum edge distance to the edge of the brick, we have this wasn't intended to be commercial, but we have a general requirement and in our documentation of 30 mils from the edge of a clay brick and 50 mils from the edge of a concrete masonry unit. In instances where you don't know where the edge of your bricks are, or you have to prefabricate steel and you don't necessarily know where the tie is going to align, if it'll be in the center of the brick, there's a few different approaches. Sometimes a statistical approach will be taken where, say, you implement 10% more anchors than what you need to account for those cases where you might hit a mortar joint, for example. Other options are sometimes site testing. An anchor site testing program will be run where you test anchors in the mortar joints or with close spaces to the edge of the bricks, just to give you a workable design capacity to use to account for those situations.
All right, thank you. All right, I think Zurich has given a bit more extra detail to his questions before. So his original question was, what is the basis for selecting the spacing of fixings when designing retrofit system, supporting the top of a wall of an old building where the footing has settled following footing repair?
Cool. So yeah, really depends on the application, whether you're going to be doing engineering calculations on that, or whether you're reverting to AS 3700, for example, for replacement of wall ties. If you're not relying on composite action, AS 3700 spacings are perfectly applicable. If you're doing something a little bit more detailed, like what you're alluding to, Zurich, you'd probably just run some numbers and ascertain what spacings you need based on the design capacities that we could provide you with for our Python anchors, for example.
All right. Hope that answers your question, Zurich. And then if not, feel free to reach out to Kieran directly after this. We've got about 10 minutes left, so I will go through a few more questions. One from Ahmed. What would be some main points to consider when debating whether to reconstruct a brick wall rather than retrofit? Understand that this is project specific, but if you have any pointers, that would be appreciated, Kieran.
It's a good question. So yeah, again, sort of depends how far gone the wall might be, and what the design intent of the element is as well as project budget, etc. Rebuilding can be more expensive than retrofitting, but yeah, really comes down to what the element is doing structurally to make a call on whether it can be utilized and repaired, maybe with the use of some additional timber structure, or demolished. But feel free to send me through the specific example afterwards, and we can take a detailed look at it together.
All right, cool. Another follow-up question from Jesse. What sort of inspection schedule do you recommend for the Python ties, assuming they can corrode over time the same as the original ties?
So good question, Jesse. So it comes down to the engineer's QA essentially, but what is typically done is, the beauty of having a mechanical screw anchor means it's reversible. So it's very easy to come along and say you might implement a plan for inspecting them every 10 or 20 years. You could come along, you could actually unscrew the ties and inspect them. And if they do have any signs of corrosion, which I wouldn't expect, you could take them out and replace them very easily. However, yeah, with the original brick ties, they're completely untreated. Usually, they don't have any corrosion protection systems on them, hence all the corrosion that occurs. With our anchors specifically, they do have a very serious corrosion protection system on them, and so we expect them to last the life of these heritage structures and outlast most of the other elements.
Nice. All right. Next question is from Robert. I am often asked about replacement of rusted out lintels under suspended masonry. Is there a system to support this beyond entirely replacing brickwork above the opening with the installation of a new lintel?
Yep. So we have solutions for lintels, whether they're concrete or brick lintels. There's been situations where with concrete lintels where all the bars have been corroded, they've removed it, they've installed some of our anchors into the brickwork, and then they've cast the concrete over the heads of the anchors. There's also the products for crack stitching out there. We have one of these. They're sometimes used for strengthening lintels as well by laying the steel wire rope along the lintel to act as a sort of the tension reinforcement of a beam. So there's various methodologies for strengthening lintels.
Great, awesome. So sounds like a lot of interest in Python products. Kieran, if you, we can definitely share your product guide with the participants after this, as we've done with the New Zealand and US webinar before. All right.
Awesome, that sounds great.
Yeah, a few more questions left. Let's see, from Avandi. For the pre-tension rod system for retrofitting brick chimney, what is the fixing method between the top plate to the chimney?
Fixing method between the top plate and the chimney, it is in compression. So I believe it was just sitting there in that test, but you could easily fix that down with some small mechanical anchors vertically into the brickwork just to hold it in place and do a calculation on the spacings and embedment that you need.
Nice. Awesome. All right. Question from Adrian. What would be the best method of fixing new structures, such as cantilevered awning, to brickwork, especially if there is a high concentrated load?
Yep, so that's something that's done fairly commonly. So if you can get enough capacity out of a standard mechanical anchor, you could have a plate with, say, 4 anchors, depending on the brick compressive strength and embedment available. You might get enough strength out of that. Otherwise, there are options where traditional anchors can't give you enough capacity, where you through bolt your awning and use a plate on the back side of your wall, engages a larger surface area of bricks and gives you an increase in pull through capacity. So plates can be a good option as well.
Nice. All right, and we're down to the last question, again from Jesse. Without waiting for failure, how would you work out if all the epoxy anchors were installed correctly or were working properly?
Good question. So as engineers, our best tool for dealing with that is QA. So often in specifications, structural specs in the past, I've seen likes of 2 to 5% of anchors must be proof tested after install. That is a good way of addressing it. And so, yeah, that's probably the most common way, is this percentage of anchors are proof tested after install to check that the installation is sufficiently done.
Awesome. All right, a couple more questions has come through from Melior. Is horizontal or vertical direction of Python anchor the only way? And what is the longest anchor do you supply? And do you have a capacity table for this?
Horizontal, they can be installed at angles, not a problem at all. Of course, if you are installing them at an angle, you're introducing combined actions, tension and shear, and so you will need to account for that by calculating the reduction in strength, and typically that's limited to 1 in masonry for the combined actions check. But certainly, particularly with steel applications, for example, connecting through the flanges of big UCs and UBs, Pythons will often be put in at an angle, so it's definitely something that's done all the time. And 100%, we have capacity tables. We've got a mountain of data for all of our fixings and every different relevant Australian substrates that you can think of. So more than happy to share that with you afterwards as well.
Awesome. A couple more questions related to Python Anchors product. First one being, is Python Anchors made from steel or stainless steel? And then, does Python Anchor have seismic ETA to C2 and pin fixings with seismic ETA?
Good questions. So Python fixings are made from high strength steel, about 1,000 MPa yield stress. The reason for that versus them being stainless is because applications, for example, your shotcrete overlays and composite action between 2 layers of masonry, it's really advantageous to have high strength steel in those situations. So you can use less anchors across the project, keep the cost down. These projects are always cost sensitive. Stainless is also very expensive. Durability wise, they've got the zinc nickel coating system, galvanic coating system on them. And we've got extensive durability testing to back that system up. And it's a highly durable coating system, about 5 times more durable than galvanization. And so, yeah, they're high strength steel and they've got the zinc nickel coating system on them, but they're not stainless. What was the second question there? Sorry, Matthew.
Yep. Does Python Anchor have seismic ETA to C2 and pin fixings with seismic ETA?
Good question. So in masonry, so C2, the ETAs really comes from the concrete world, and there's no such requirement for having an ETA or C2 rating in masonry substrates for retrofitting them. So it's just not a requirement and not needed. However, we do actually have another anchor, which is specifically for hollow core floors, unrelated to the masonry space, the masonry work that we do, and that does have a C2 rating. we've actually got a really interesting presentation I can share by one of my colleagues, Rob, all about C2 ratings and how they work, which I'd be happy to share the link to as well, because it's super interesting.
Yeah, awesome. We have a few more questions. Kieran, are you happy to run this through, or do you have somewhere else to be?
No, not a problem.
All right, let's do it. All right, so a question from Tony. Have you worked on Masonry retaining wall project? And if you have, can you please share some experience on them?
Limited experience myself personally with Masonry retaining walls, although I know they have, Pythons certainly have been used for them. Our plated connections can be an option. The plates, you can get some nice architectural plates to tie back your retaining walls even into ground anchors. And then there's the various standard strengthening measures for outer plane strengthening, utilizing additional structure if you need to, like steel or timber connections to brace the wall out of plane for retaining walls. So those can be some good options.
All right. And then a question from Ersin. When crack stitching, how do you cater for the central skin of a 3-skin brick wall?
The central skin of a 3-skin brick wall. So you can grind out the mortar joint as far or as little as you need to lay your crack stitching wires in. For a multi-wire thick wall, I'd suggest grinding out half, maybe, at least 1 brick depth. And you can lay as few or as many wires into the joint as you wish to strengthen it up. Maybe half the depth of the wall would be sensible. Lay 2 or 3 stainless steel wires in, epoxy them up, and that would give you a robustly stitched crack.
Nice. All right, let's do one last question again from Jesse. Has there been any studies on that coating to ensure if it remains in place during installation?
Yep, there has indeed. And so that's a galvanic coating rather than a barrier coating. So it doesn't just rub off on install. In saying that, we've done an extensive study into the durability of the coating system. And one of the tests that was done in that study was an anchor was installed, or anchors were installed and removed numerous times to essentially intentionally damage the coating, and then subjected to extensive salt spray exposure. And I can share our durability report covering that and how it performed, and it all performed really well, even with the multiple installs and removals.
Perfect. All right, that's all the questions that we have. Well done, everybody, and thank you, Kieran, for going through all of that one by one. All right, so that is the end of our session today. You will all receive an email right after this with a quick survey to share your feedback on what you find valuable from the presentation and what you want us to improve next. And also make sure you just say yes or no if you want a certificate of your participation for this webinar as well. We will try to get the Python products guide from Kieran and send it over to everyone as well. And then if you have any further questions about the product or your projects, feel free to reach out to Kieran per his contact details. I will include this in the email as well. All right. Thank you, everyone. And thank you, Kieran, for your time. We will have a webinar next month as a follow-up to this on Holocore Anchorage of Services and Bracing. So make sure you register for that if you have not. Enjoy your afternoon. Thank you again.
Thanks, Artie. Thanks, everybody. Appreciate your time.
Thank you. Bye-bye.
Yes.